Good evening, ladies and gentlemen. All right, so we're going to be continuing what we left off with in our last video by going through the workflow of using your own simulations, making your own simulations. So let me get back to section 3.2. We're going to be looking at the simulation scene in 3.2.2, the P-band vegetation analysis. Okay, so for this simulation, we're going to be assuming that we're having a P-band signal, as stated here, and that we're going to be traveling through a forest canopy. So that's going to define our vegetation cover. Our P-band transmitter is going to have variable orientation, so its position is going to be changing within the sky. And our antenna pattern is going to be user-defined this time. That's going to be the kind of new guy on the block here. So the simulation setting is going to be snapshot again, and the ground structure again will be, we're going to assume that it's single layered to keep things simple for this one. Okay, so yet again, let's look at SCoBi, give this guy a run, and let's just select forest because, again, you're not forced to, but it goes ahead and sets things up pretty simply for us. Okay, so as the problem stated, we're going to be looking at a snapshot simulation with a variable orientation. So let's see that we have that checked here. Snapshot, variable orientation, and signal layer. Alright, so we're going to go back and look at the default file that was listed there. Alright, so we're in the source, we're going to go to input, input configuration, and I believe it was this one here. Right, so this is the same sheet that we were looking at in the last video, so I'll give a quick recap. The name of the sheet is dynamic. The name of the sheet doesn't matter, but the order does. So if I switch this, then things get wonky. So always have your dynamic or your changing variables as the first spreadsheet in your input configurations file. Since we said that we're having a changing orientation, we need to change our incidence angle, our theta values in the first column, and our phi values in the second. So these can be an arbitrary number. I could have 72 here. It doesn't necessarily have to follow certain patterns. This could be 26. And this would change the number of simulations that are run. So let me get rid of those just for simplicity's sake. And for this third column, we're going to be varying the RMS height of our surface layer. And for the final one, we're changing the effective volumetric soil moisture of our soil profile. Again, last time we looked at this, and the value or the number of simulations that are going to be run will be the number of variables multiplied together for each of these different columns. So this is going to be 7 times 2 times 3 times 8, which is about 336 if I remember correctly. Alright, so the variables that don't change, since this is one single soil moisture profile, are going to be your soil textures throughout each of these simulations. So for all of these simulations, we're going to assume that our soil is 80% sand, 7% clay, and the bulk density is 1.25 grams per cubic centimeter. These variables, along with the soil moisture and the wavelength of our signal of opportunity transmitter and RMS height, will all interplay together to calculate the effective dielectric of the single soil moisture profile. And that's that for this spreadsheet. Next up, we need to look at our vegetation. So this one's going to be forest, so this one is going to be a little bit different. So as stated before, we have two different spreadsheets right here, layers and kinds. Again, order matters, names of the variables do not. So with layers here, we are putting the order of our layers, and we're declaring what our constituent scatterers are and the kind of scatters as they are that we're going to define in the kind sheet. So again, if I were to draw this guy out, we'll have our air layer at the top. Let's look back here. Layer 1 is going to be 2 meters thick. The one below is going to be 4 meters. And the two below that are going to be 3 meters and 4 meters. And we'll then have our soil moisture profile. Alright, so layer 2, layer 3, sorry, my handwriting's a little cramped right here, and that's all my fault. Okay, so this is essentially what's being described, and by declaring these variables here, we are describing the dielectric of these different layers. So let's go into declaring these variables. So here we are listing out our different kinds of variables. L indicates that we have a leaf, B indicates that we have a branch, and T indicates that we have a trunk. The first row right here shows that we have 11 of these leaves per cubic meter. Branches we have, if you kind of think about that, 0.016 of these per cubic meter, and so on and so forth. I'll have to go back and look in the documentation here, but right. So since this is a leaf, we're describing the semi-major axis for this variable, and the rest of them we're describing the bottom cylinder, the bottom cylinder's radius. That's right. That's what this says here. The next row indicates the minor axis for a leaf, since it's a disk, and this one is the top cylinder's radius, and this indicates the what was it? Right, thickness of the disk and the length of the cylinder. The next two variables describe our dielectric values of the components of these scatterers, and these angles below describe the orientation of these scatterers within the dielectric relative to the zenith. Alright, so that's that for the vegetation file. Alright, and so the fun part about this simulation that we're discussing for the P-band vegetation analysis, we are assuming that we have a user-defined antenna radiation pattern. So if we look back at our GUI, we see that we have user-defined set up right here, and we can find a user-defined, or an example of user-defined antenna radiation pattern right here under receiver antenna pattern, and we'll open it up right here. And so this sheet with lots of numbers and no headers defines the normalized, I believe it's called normalized voltage pattern for your receiver antenna. So what this shows is for port 1, denoted as XX, or the, if I'm not mistaken, this is in terms of linear polarization, so this could be considered vertical, and this horizontal polarization in the two sheets in between are the crosstalk, or the cross polarization matrices for each of these ports. Okay, so values along the rows, let's see, let's count these. So we have 61 values along the rows, and we have 121 values along the columns. Actually, I got those mixed up. So we have 61 columns and 121 rows. So along the top, along the columns, since we have the lower number, that corresponds to the theta values for our antenna radiation pattern. So if we were to go here, again, the theta values corresponds to, it needs to have n+1 and the phi values generally have 2n+1 parameters. So considering that we have 61 values here, that shows that n is 60, both of these, and by taking that and dividing the number of theta values, which is generally 180 degrees over 60, that shows that we have 3 degrees of resolution for our antenna radiation pattern here. And same goes for our phi, which would be 360 over 2n, which would be 120, which again shows that we have 3 degrees of resolution here. So for this sheet, you need to define your normalized voltage pattern for your port 1, port 2, and the cross polarization between port 1 and port 2, respectively. We are developing functions that allow you to do this, hopefully within MATLAB and its antenna toolbox pretty soon. We've developed tools to do this with CST's antenna simulation tools as well. I'm not sure if that's included with SCoBi Veg at the moment, but if not, it'll definitely be available before too terribly long. Anyway, so this is just sort of a brief update on current methods, or the general idea behind setting these parameters up. Alright, so that is the antenna radiation pattern. So once you have that defined, all you have to do is run through the GUI real quick. So again, we have named this something that's relevant to what you're doing. So forest P-band MS 39759, I don't know. And it's not that. Okay, this is a snapshot like we discussed earlier, so that's checked. Vegetation, that's good. P-band at 370 megahertz, that's right in P-band's range. Range to Earth center, as we discussed earlier. So all of these variables are in line. Again, this is a single layered profile, so that's fine. And our dielectric model checks out. You can define this if you're interested in your received power. And yeah, so as long as you make sure that your configuration inputs file is pointed to the right location, as is your antenna pattern file and your vegetation inputs file, save your changed inputs, and you're good to go.